A 450 turn solenoid, 23 centimeters long, has a diameter of 2.2 centimeters. A 13 turn coil is wound tightly around the center of the solenoid. If the current in the solenoid increases uniformly from 0 to 5.2 amps in 0.52 seconds, what will be the induced EMF in the short coil during this time? We've written Faraday's law in two forms. The first form is the voltage induced on a single loop in the presence of a varying magnetic field, and this voltage is negative the time derivative of the magnetic flux going through the loop. The second formulation of Faraday's law is if instead of a loop we have a coil. The difference between the loop and the coil is that a coil is effectively many loops in series with one another. As a result, the coil has n times the voltage of any single loop. In the problem at hand, a long coil with 450 turns engages a second coil which is tightly wound so that the second coil has 13 turns. The current in this problem is the current in the long coil. However, the voltage that we're to calculate is the voltage across the short coil. For that reason, in our Faraday's law, we recognize that the N preceding the formula will refer to the short coil, while the flux will refer to that created by the long coil. We'll begin our calculation by determining the magnetic flux. As always, the flux of any field is that field times the area, and the formula for the magnetic field inside a solenoid is mu0 times the turn per unit length times the current. Since our solenoid has a cross-sectional area which is a circle, we will use pi r squared as the appropriate area. We see that every term in this expression is time independent except for the current. Therefore, the deflux dt will be equal to mu0 n over L pi r squared times the time derivative of the current. Finally, to get the voltage in the coil, we need to multiply the previous expression by n. I'm going to draw this n in green because this is the n of the short coil, which is 13, while writing the rest of the expression in black. We can plug in the numbers, wherein we carefully use 13 for the first n, 450 for the second n. We're certain to change the unit of centimeter quantities into the meters, and also we recognize that since the 2.2 centimeters given in this problem was the diameter, we need to divide that by 2 to get the radius. Finally, for the time derivative of the current, we take the change in current, which was 5.2 amps, divided by the time interval, which was 0.52 seconds. The result of the calculation is 1.21 times 10 to the minus 4 volts. And this completes our calculation.